Okay, so in this video, we are going to sketch a graph of this degree 4 polynomial. So as always, find your first and second derivative. That will help you find the critical and inflection points of the graph. So y prime, the first derivative, will give us 4x cubed plus 12x squared minus 16. Look at your second derivative, y double prime, differentiate the derivative, which will give you 12x squared plus 24x minus 0. And you know you will be looking for critical points and inflection points, so you have to find values of x that will make the derivative 0 or undefined. Same goes for the second derivative. As they're both polynomials, they are always defined, so we have to look for zeros of the first and second derivative. Looking for zeros of a polynomial means we want to factor the polynomial. Let's factor the easier one first, the second derivative. There's a common factor of 12x. If we pull out the 12x, we are left with x plus 2. Look at the first derivative. Well, we can at least factor a 4. And if we do so, we have 4 times x cubed plus 3x squared minus 4. But this is a cubic polynomial, so it's not clear how to factor a cubic polynomial, but remember the zero theorem. If you look for a factor of a polynomial, you can instead look for a value of x that makes the polynomial equal to 0. Look at the coefficients. This is 1, this is 3, and this is 4. 1 plus 3 is 4, minus 4 is 0, and this can be done if you take x to be equal to 1. Plug in x equals 1, you get 1 plus 3, 4 minus 4 is 0. Because this cubic polynomial is 0 when x equals 1, x minus 1 has to be a factor. And let's find the missing factor with long division. Let's divide this cubic by x minus 1. So, x squared times x is x cubed. Multiply by x minus 1, and you get x cubed minus x squared. Subtract. This cancels, and you're left with 3x squared negative negative positive x squared. So 4x squared minus 4. Now you repeat. 4x times x is 4x squared. Multiply through, you get 4x squared negative 4x. Subtract. 4x squared minus itself is 0. Negative negative gives a positive 4x minus 4. Plus 4 times x is 4x. 4 times negative 1, negative 4. Subtract and you get 0. Therefore, x cubed plus 3x squared minus 4 is x minus 1 times this quadratic polynomial. And this you can factor by inspection. It actually is, so you look for two real numbers whose product is 2 and whose sum is, whose product, I gave the answer away, whose product is 4 and whose sum is 4, and this is obviously 2 and 2. X squared plus 2x is x squared plus 4x plus 2 times 2, 4. There you go. And so we have factored our first derivative. This cubic is x minus 1 times x plus 2 times x plus 2, therefore x plus 2 squared. Okay, so now we have factored our first derivative, our second derivative. So the first thing we look for, if possible, are zeros of the function. The zeros are the x-intercepts. Values of x where the function is 0. But if you look at the function, is a quartic polynomial, and it's really not obvious what are possible zeros of this function. And actually, the zeros tend to be irrational numbers. So when you have a function and it's getting a little hard to figure out the zeros, and here it's really hard, just don't bother. Only find the zeros if they're fairly easy to find. If it's too much work or just you can't do it, don't waste too much time, just move on. So we're saying the zeros. We'll see when we sketch other points, we will have two zeros of this function, but as I've said, they are irrational numbers and very difficult to find, so we don't bother. We now look for critical points, or if you want, the y-intercept of the function. That is where the function crosses the y-axis, therefore the y value of the function when x is 0. This is very easy to find. Plug in x equals 0, and you get a y value of 2. So the y-intercept is quite simply y equals 2. Now let's look for critical points and inflection points. As always, I write CP for the critical points. Since the derivative is a polynomial, it never is undefined. So the critical points are values for which the second derivative is equal to 0, in this case. This will be easy to find since we have factored our first derivative. Y prime equals this. And this can only be 0 if x is equal to 1 or x is equal to negative 2. So we only have two critical points. X equals 1 or negative 2. What about possible inflection points? Well, again, oh, my bad, this is not y double prime. This is y prime, right? We're looking for critical points. Critical points are zeros of the first derivative. And this is what we looked at. The first derivative is 0 if x equals 1 or x equals negative 2. Sorry about that. Now that we're looking for inflection points, this is the second derivative being 0 or undefined. As it is a polynomial, it never will be undefined. So we look for zeros of the second derivative. Well, let's look back. This will be easy because we have factored our second derivative, 12x x plus 2. And so the second derivative is 0 if x equals 0 or x equals negative 2. And there is something interesting here because negative 2 is simultaneously a critical point and a possible inflection point. Okay, so now that we have found our critical points and possible inflection points, we try to, as always, to classify the critical points. Will they be local maximum, minimum, or maybe something different? Well, let's classify x equals 1 first. As always, we look for the second derivative. We know that at x equals 1, the first derivative is 0. Therefore, the curve is flat around x equals 1. To see if we have a local max or min, we consider the second derivative at x equals 1. And again, we don't care so much for the value as much as the sign of the second derivative. So here's the second derivative. If we plug in x equals 1, we get 12 times 1 times 3. Which happens to be 36. We don't care that it's 36 as much as the fact that it is positive. So the second derivative is positive, so the curve is concave up at x equals 1. Since the curve is flat at x equals 1, the derivative is 0, and the curve is concave up, x equals 1 is a local maximum, local minimum. And so we can visualize graphically what the curve may look like, or will look like actually around x equals 1. Again, we don't have here an accurate sketch, just a feeling for locally around x equals 1, what the curve will actually look like. Assume the y value is positive. So at x equals 1, the derivative is 0, the curve is flat. And because it is concave up, it will look something like this. Concave up, and the derivative is 0 at 1, and so the tangent line is horizontal. And so at x equals 1, the curve will have a local minimum. So we were able to classify our first critical point with the second derivative. Let's see if we can classify the second critical point with the help of the second derivative. Let me rewrite the second derivative as a reminder. Our second derivative, y double prime, is 12x times x plus 2. And we are trying to classify the critical point, that is x equals negative 2. Well, so we're trying to figure out if the curve is concave up or down at x equals negative 2, therefore if we have a local minimum or a local maximum. Evaluate the second derivative at negative 2, and what you notice is the second derivative at negative 2 is equal to 0. And this gives us nothing. If the second derivative is positive, the curve is concave up. If the second derivative is negative, the curve is concave down. If the second derivative is 0, we get no information. So the classification fails at negative 2. So the question is now, well, how do we figure out what the curve looks like locally around negative 2 if our classification exactly at negative 2 fails, because the second derivative is equal to 0. And this is actually very easily fixed if we look slightly to the left of negative 2 and to the right of negative 2. Let me remind you that the first derivative was 4 times x minus 1 times x plus 2 squared. So let's now see how we can still fix this problem, how we can know exactly what the curve looks like around x equals negative 2. This is your x-axis. Suppose this is the point negative 2 for x. And just for argument's sake, we'll assume that the y value is positive. Okay? We have the only way to figure out what the graph of a function looks like is to accurately portray it around its critical points. So we have to fix the problem. Well, all you have to do is look at one point close to negative 2 on the left, one point close to negative 2 on the right, and look at those 2 points, the value of the derivative and the second derivative, and you will know exactly what the function looks like around this point. Keeping in mind that at x equals negative 2, the first derivative is equal to 0. Let me write it here. Y prime at negative 2 is equal to 0. And why is this important? Because if the derivative at negative 2 is 0, the tangent line is horizontal, so the curve will be flat around this point. Let's look now for a value really close to negative 2, but from the right. What will be the sign of the derivative and the sign of the second derivative? So, if x is really close to negative 2, this is always positive. Roughly negative 2, negative 1 will be roughly negative 3, so that's negative. And because we have a square here, this will always be positive. So we have a positive times a negative, so the first derivative is negative, close to negative 2. Therefore, if the first derivative is negative, the function is decreasing. To the right of negative 2. What about the second derivative? We have the term 12, which is positive, times x. X is very close to negative 2, so this is negative. What about x plus 2? Let's do it here. You say this is negative 2. we are taking a value of x that is to the right of negative 2. So x is a little bigger than negative 2. Add 2 on both sides, therefore 0 is less than x plus 2. So x plus 2 is positive. So to the right of negative 2, x plus 2 is positive. So this is positive. This is positive, but x itself is really close to negative 2. Therefore, x is negative. So you have a positive times a negative times a positive. The result is also negative. So to the right of negative 2, the second derivative is negative. Therefore, the curve is concave down. And now think of it. This tells the whole story. The curve must be decreasing. Well, there are only two ways to have a decreasing curve. It has to be decreasing concave down or decreasing concave up. But we know that the curve is concave down, so it cannot be this one, so it has to be this one. So you see, to the right of negative 2, the curve must look something like this. And we know that exactly at negative 2, the curve is flat because its derivative at negative 2 is 0. So we'll piece this graph at negative 2, keeping it at negative 2, the curve is flat, and it's decreasing and concave down. And this is what the graph looks like around negative 2 to the right. Well, let us now repeat, looking at what the graph may look like around negative 2, but now to the left. So again, we need a sign of the first and second derivative. You have a value of x that is close to negative 2, but to the left. This is a square, always positive. 4 is always positive. X is very close to negative 2, so this is very close to negative 3. So you have a positive times a negative times a positive. The result is negative. Therefore, to the left of negative 2, the curve is decreasing. What about the second derivative? Well, now this will be a little different, right? Because we are looking around negative 2, but to the left. And so x is to the left of negative 2, therefore slightly smaller than negative 2. Add 2 on both sides, and you get that x plus 2 is now less than negative 2 plus 2, which is 0. So to the left of negative 2, x plus 2 is negative. So now look back to the second derivative. X plus 2 is negative. 12 is positive, but x is very close to negative 2. Therefore, x is negative. So you have a positive times a negative times another negative. So positive times negative is positive. So to the left of negative 2, the second derivative is positive. So the curve will be concave up. Well, let's see. The curve is decreasing to the left of negative 2. There are only two ways in which a curve can be decreasing. It is either decreasing concave down or decreasing concave up. We know it's concave up, so it can't be this one. So the function on the left of negative 2 must look something like this, keeping in mind that at negative 2, the derivative is 0, so the curve is flat here. So we're going to piece this portion of the graph to the left of negative 2. So concave up decreasing, and at negative 2, the curve has to be flat. And now we know what the curve looks like around negative 2, and now we're good to go. We have classified our first critical point, x equals 1, as a local minimum. The classification at negative 2 failed, but simply by looking at the first and second derivative to the right and the left of our point, we were able to figure out what the curve looks like very accurately around the point negative 2. Concave up, decreasing, concave down, decreasing, and because the derivative at negative 2 was 0, the curve there is flat, so its tangent line is horizontal. And now we're good to go. We can produce a table of values. I'll jump to another page. Again, we look at only the points of interest initially. If we need to add more points, we will, but only if we have to. The first point we found was the Y-intercept, which was x equals 0. And if you recall the function, I'll write it here, y was equal to x to the 4 plus 4x cubed minus 16x plus 2. So if you plug in here x equals 0, you get y equals 2. The zeros we said were too hard to find, so we didn't bother. We had two critical points. The first one, x equals 1. The second one, x equals negative 2. If x is 1, you'll get 1 plus 4, 5, minus 16 minus 11 plus 2, negative 9. So when x is 1, y is negative 9. The other critical point, x equals negative 2. If you plug in here negative 2, you'll get 16. Negative 8 times 4, negative 32. 16 minus 32 is negative 16. Plus 32 plus 2 will give you plus 18. That's taking care of our two critical points, and interestingly enough, our inflection points were also 0, x equals 0, and x equals negative 2. So there are only 3 points of interest here. Let's now sketch the graph of our function, and here the axis will not be up to scale because you see we have values ranging from 2, negative 9 to 18, and in x it's 0, 1, negative 2. So again, don't bother with a ruler making a graph that is up to scale. Axes are up to scale. Just capture the key features of the graph. We're looking x around 0, 1, negative 2. So this will be fairly symmetric around 0. And we go roughly from negative 20 to positive 20. So let's go like this. Sorry, from negative 10 to negative 20. So we go roughly, say, midway. And again, my graph will not be up to scale. That's not important. What is important is we capture the key features of the graph. All right, so our 3 points, x equals 0, y equals 2, x equals 1, y equals negative 9. So say this is x equals 1, y equals negative 9, and x equals negative 2, y equals 18, so it's twice of that. So it'll be roughly here, roughly here. And you can label only those points. So this is the value. Afterward, we'll write a 2 here. This is an x equals 1, and this is an x equals negative 2. This is a y equals 18, and this is a y equals negative 9. Okay. Well, as always, we handle first locally the graph around the critical points. Let's handle x equals 1. If you go back to our classification, we know exactly what the graph looks like around x equals 1. We found that x equals 1 was a local minimum. So around x equals 1, the graph will look something like this. So it's flat there. We have our local minimum. Not the greatest picture, but Oh well. And we also have figured out what happens in our next critical point, which was -2. If you go back to our classification, this was a bit more work, but around -2, the graph looks like this: concave up, decreasing. At -2, the curve is flat, and then concave down and decreasing. So we'll glue this picture onto the point -2, 18. So concave up, decreasing, the curve is flat, then it's still decreasing but now concave down. And now I claim that we're essentially done. Let's look to the local behavior of our graph. So let's figure out what happens here. What was the point x equals 0? If you remember, x equals 0 was not just the y-intercept, but it was also a point of inflection, right? If you go back, the two possible points of inflection were x equals 0 and x equals -2. So is there a change in concavity at x equals 0? Well, let's see. The curve here is concave down. Go to the right of 0, the curve is now concave up. So you see between -2 and 1, the curve does change concavity. It goes from concave down to concave up. And if there ever is a change in concavity, it has to happen at a possible inflection point. So it has to change concavity exactly at this point. So here I'll have to correct my target a little bit. The curve is concave down and decreasing until we hit this point, our possible inflection point. And then, as soon as we go beyond x equals 0, the curve will become concave up. And again, I'll fix my target here. And the great thing is, to the right of 1, there are no critical points or inflection points, so the curve will never change its behavior again. It is concave up, it will remain concave up forever. It is increasing, it will be increasing forever. The only question left is, will we have a possible right horizontal asymptote? So we are asking what happens to y when x goes to positive infinity. Well, let's see. The limit as x goes to infinity of y, which is x to the 4, plus 4x cubed, minus 16x plus 2. Again, we have a polynomial. We know that when x is very large, the only term that matters is the largest power of x, which is x to the 4. As x goes to infinity, x to the 4 goes to infinity, so the function blows up. So we do not have a right horizontal asymptote. As x goes to positive infinity, y will also go to positive infinity. So it will keep increasing and being concave up forever. And you see that we have a real 0 here. But again, it was too hard to find, so we don't know exactly where the function crosses the x-axis here. But we can feel that it's roughly between 1 and possibly 2. And that takes care of the behavior to the right of 1. Well, the same can be said to the left of -2. To the left of -2, there are no more critical or inflection points. So beyond -2 to the left, the curve will never change its behavior. It is decreasing and concave up. It will be forever decreasing and concave up. Once again, we have a question. Will we have, as we let x approach negative infinity, will we have a left horizontal asymptote? Well, again, we are asking what happens to the function y as x is approaching negative infinity. Once again, we have a polynomial, so only the largest power of x matters, and because 4 is even, as x goes to negative infinity, x to the 4 goes to positive infinity. And so we do not have a left horizontal asymptote. As x goes to negative infinity, y blows up to positive infinity, which was rather clear from the shape of the graph here. So it's decreasing and concave up forever. And we now have captured the graph of x to the 4 plus 4x cubed minus 16x plus 2 very accurately. Every point that was important is captured. And now let's label our points. Let's see what we had. This point right here, x equals 0, was a possible inflection point, and indeed it is. The curve is concave down to the left of 0. We hit 0, and the curve becomes concave up. So this is a real inflection point. X equals 1 was a critical point, a point where the derivative was 0, and as we can see clearly we have a local minimum. But something is interesting here. Not only is this a local minimum, it actually is a global minimum. Look at the picture. Nowhere will the function attain a smaller value than at x equals 1. So not only is -9 a minimum value around x equals 1, it actually is the absolute, the global minimum value attained by the function. There are no other x values that will give you a y value smaller than -9. So we have not only a local minimum, but a global minimum. And -2 was a very interesting point. It was simultaneously a critical and possible inflection point. So we know this is a critical point because at that point the derivative is 0, so the curve is flat. Let me just kill this part. At that point the derivative is 0, so the curve is flat. It is neither a local min or local max, right? Move to the left of the point and you have slightly larger y values. So this point can't be a max. Move to the right and you get slightly smaller y values. This point is neither a minimum. This is not a local max or a local min, but it is worth mentioning it is a critical point because at this point the curve is flat. So this is a critical point, but nothing more. And is it an inflection point? Because not only was -2 a critical point, it was also a possible inflection point. So does concavity change at -2? Well, let's see. The curve is concave up, 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 up. We hit -2, and the curve becomes concave down. So indeed, there is a change in concavity. So not only is x equals -2 a critical point where the curve is flat, it also is a real inflection point. And now we have sketched a graph of this quartic polynomial very accurately. Every key feature of this graph is captured. We have a global minimum at x equals 1. The minimum value attained is y equals -9. We have an inflection point at x equals 0, where the curve goes from concave down to concave up. We have a critical point at -2, where the derivative is 0, so the curve is flat at this point. And we also have at -2 an inflection point because the curve went from concave up to concave down. And as x goes to positive infinity, y shoots up to positive infinity. And as x goes to negative infinity, y also shoots up to positive infinity. And that's the graph of this quartic polynomial, again, done by hand. And you see it really was not obvious from the beginning, just by looking at the equation of this polynomial, that the graph would look something like this. I don't think you could have guessed that the graph of this would be exactly this. And the great thing is we have a really non-trivial graph, and all we needed to do to produce this graph was to find the first and second derivative.